have joined. Awesome. So thanks everyone for joining. Good morning. Today it is a pleasure for me to introduce Carolina Cuesta Lazaro as our seminar speaker. So Carolina did her undergrad at Universidad Autónoma de Madrid. Then she moved to the Ruprecht Karls University in Heidelberg for a master's. She's now finishing her PhD in the Durham University under the supervision of Baju Li, where she's working on the theoretical development of statistical methods to test the theory of gravity and also the nature of the accelerated expansion of the universe. She also has work experience outside of astrophysics, having worked as an applied scientist intern at Amazon, as a data scientist intern at IBEX Innovations. And as I understand, she has also been working on modeling COVID-19 spread using very exciting statistical techniques as well. So today she will be telling us about redshift-based distortions in a nutshell. Carolina, we are very happy to have you as our speaker, so the stage is yours.
Thank you very much, Enrique, for the introduction, and thank you for inviting me. It's a pleasure to be here. I know normally people say that it'd be a pleasure to visit in person, but as Enrique said, maybe not now, that is minus 20 degrees. In the summer, I'll be very happy to visit. But
before you begin, are you happy to be interrupted with questions during the talk?
Yeah, please do. I've never spoken for 50 minutes, so I hope it's not the first time. Feel free to interrupt, ask questions or comments, whatever you feel like. But yeah, today I'm going to be talking about galaxy redshift surveys and how we can use them to extract information about the laws of gravity and the cosmological parameters. And especially I'll put a bit of emphasis on how we can use machine learning to probe scales that we couldn't do before. But let me start with a bit of context. So this is a summary of the standard cosmological model that's been developed over the last 30, 40 years, which basically assumes general relativity is the theory of gravity and the universe is homogeneous and isotropic on large scales. And what is so elegant about this model is that it only really has 5 parameters. So all the information about the universe is contained in these 5 parameters. 2 of them that will define the statistical properties of the initial conditions, and 3 of them that will be responsible for the dynamics and how those initial conditions grow into the structure that we see today. Now, as elegant as it is, it's also highly suspicious because many of those parameters we don't really understand, mainly dark matter and dark energy. So this is why most cosmologists today work on trying to break this model. So finding observations that don't comply with this model so that we can get some guidance on what is missing. How can we learn more about what is producing the accelerated expansion of the universe, or what is the nature of dark matter? However, this whole style model is still very successful, especially at explaining the early universe. So you see here a picture of the cosmic microwave background radiation that is basically giving us a map of the density in the universe when it was 400,000 years old. I'm going to define this overdensity delta as the difference between the density at a point and the average density of the universe divided by the average density. That means if a point has the average density, which is this light blue here, that would be an overdensity of 0. And in a dark region where the density value is very low, close to 0, that would be close to -1. And this delta is going to be bounded by -1 because the density can't be smaller than 0. So what's interesting about the early universe is that this overdensity can be modeled as a linear function of the initial density field. Because the perturbations are still small, so we can kind of tailor expand what we call perturbation theory, the density field. And it gets even better because it's also Gaussian distributed. So you can see here a histogram that looks like a Gaussian of the values of this delta. It really is a field in space, right? So you can think about it as a multivariate Gaussian that is taking different values at different places, but they're still Gaussian distributed. So it would be characterized by a mean and a variance. Higher order moments of a Gaussian distribution are not independent. The mean by definition is going to be 0 because we found a convenient way to define it. And the variance of the second order moment is what we called the 2-point correlation function. So this will tell us how the value of the field at the point is correlated with the value of the field at a different point. And this will be defined by their distance. So you can think of the fact that if you're looking at points that are close in space, they will be highly correlated because of gravitational attraction. Whereas if you look farther away, they're likely to be less correlated. But what is very important about this Gaussianity is the fact that if we were to constrain our theory of gravity using the whole field of the cosmic microwave background, we will find the same constraints as if we use these one-dimensional functions. So this is a very useful, this is just an optimal summary of the map. It turns out that it's easier to compute the Fourier transform of this object that we call the power spectrum. And this is how it actually looks like for this map that you see here. I'm not going to go into the details of why it looks in the way it does. I just want you to take the message that it is an optimal summary for the map here, and that means that we can predict the value of this power spectrum given the cosmological parameters and compare it to the observed one to get really tight constraints on how gravity should behave and the value of the cosmological parameters. This is all for the early universe. So this is what cosmologists have been doing for maybe 20 years, try to understand this early universe and get constraints on cosmology. Now the question is the late universe compatible with this picture? And there are many different ways in which we can probe the late universe. You have here a list of them, but it's definitely not exhaustive. Gravitational waves, gravitational lensing. But today I'm going to focus on galaxy clustering. So these are three-dimensional galaxy maps of the local universe and their clustering properties. So the statistical properties of this map will depend on the underlying laws of gravity and the cosmological parameters. And the idea is that if we study these and then compare them to what we obtained by looking at the cosmic microwave background, we can check the compatibility of the two and see whether there's something missing in the picture of cosmology. So this is all great, but all the good things we had in the early universe are going to go away. So it was, first of all, linear. If we look at the late universe, it's going to be non-linear. So that means we can't express the value of the density field at a point as a function of the initial density field. It's a linear function of the density field, which makes calculations much more involved. And, well, yeah, basically it means perturbation theory is not as accurate as it was in the first place. It actually is really inaccurate on small scales. And the second issue is that the histogram is not Gaussian anymore. So as voids become emptier and peaks grow, the distribution becomes non-Gaussian. You can see that as a distribution being bounded by -1, right? It can't really grow linearly. And this is an issue because when we try to summarize our observations in one-dimensional functions, for the case of the late universe, this is not an optimal summary. So here I'm showing the two-point correlation function of the simulation. And this won't be an optimal summary of the galaxy map you had here. So it means we're losing information by doing this step. But it is, of course, easier to produce constraints on the summary than it is at the field level. So this is a further issue that given that the late universe is non-Gaussian, the second moment is not an optimal summary. And what I will argue through the talk is that machine learning can be a solution to both problems. So first of all, it can solve the issue with producing nonlinear predictions by training models on n-body simulations. So this is something that's already been done before. So more people have done it in the past and actually applied it to data. So there's something we know works. And secondly, we can use machine learning to extract the cosmological information in the field instead of summarizing the data with handcrafted statistics. So I'm going to only talk a bit about that last aspect by the end of the talk and some ideas I'm trying to develop. But I'm going to be focusing on how do we produce these nonlinear predictions. And for now, we're going to go back to galaxy clustering. So we have here a telescope that is mapping the universe and is mapping all galaxies' positions. Ideally, it would be X, Y, and Z. But what we measure actually is an angle in the sky and a redshift. Now, if the universe is expanding, this redshift will be mainly cosmological in origin. So if we know how the universe has been expanding as a function of time, we can translate redshift into distance. However, galaxies are also moving. They have their own peculiar velocities. Therefore, the redshift will have a contribution that is Doppler in origin. If we ignored it, we will actually be inferring the wrong positions of galaxies. And this is actually what we do. So I will be calling these positions the redshift space positions, which is what you get from a galaxy survey. And the original positions, the true positions, will be called the real space positions. So now this sounds like a headache and something very hard to model, and it actually is. But it turns out that it's a good thing because it allows us to explore the velocity field. Otherwise, we will only access the density field, but these perturbations allows us to really probe what's happening with the velocities. And that's important because that allows us to test modifications to the laws of gravity. So these velocities are generated by the gravitational potential of the galaxy around it. And that's something that will be modified by alternatives to general relativity. So if we go back to general relativity, so here you have the Einstein's equations that relate the space-time geometry to its energy content. And we have the usual suspect here, lambda, which is producing the accelerated expansion of the universe. Now, theories that try to understand the nature of the acceleration and generalize it so that we can see whether this is really a constant add new degrees of freedom. So they either make this constant change with time, these are dark energy models, or they change the way that space-time geometry reacts to the energy content, normally by introducing scalar fields that will mediate additional forces. So these are normally called modified gravity models, and the additional forces are called fifth forces. And what is interesting for us is that these fifth forces will modify how structure grows in the universe. So you can think about an overdensity and how it grows as a competition between gravity, trying to pull things together, and the expansion trying to pull them apart. If we introduce additional fifth forces, that balance is going to change. And the hope is that we'll be able to detect it through galaxy surveys, and especially thanks to redshift space distortions. Now, how do we do that? So I said that the perturbation theory is not going to work. So we need to resort to n-body simulations. You have here a picture of the dark matter density field generated by an n-body simulation. Here I say dark matter because we really are only simulating dark matter. So you have millions of dark matter particles and how they interact through gravity, but you don't simulate anything else that is not gravity. Now, this will depend on your cosmological parameters that you can vary and get different dark matter density fields. But there's no way we can compare these directly to observations, because what we observe is the positions of galaxies and not dark matter particles. It'd be a good thing, but we don't do that yet. So we need a way to either simulate how galaxies form, which is something that it's there isn't a complete picture of how to do that yet. So hydrodynamical simulations, their results still depend on the particular implementation and how you model the baryonic physics, which is way more complex than gravity is. So there's no final solution to that problem. That's why in cosmology, the current approach is to have a very flexible and general model of how galaxies might form, and then hope that we can marginalize over it to get the cosmological constraints. So it's kind of saying, well, we don't really care about how galaxies form. Can we just allow for every possible model and then ignore it? Of course, there are trade-offs that you make, because if your galaxy formation model is very flexible, then you're gonna lose power on the cosmological constraints. So we want to be in sort of a middle ground. And today we're going to be using what's called halo occupation distribution models, or HODs, which do some simplifying assumptions to produce galaxy maps from dark matter fields. And the assumptions is that we can detect bound structures within the simulation. So these are dark matter particles that are bound to the same structure that we call dark matter halo. And these will be the hosts of galaxies. Now, there'll be two types of galaxies: central galaxies that one halo might host just one of them, and it will live at the center of the potential world. And the mean number of centrals that a halo will host will depend on its mass. So the more massive you are, the more likely you are to host a central galaxy. And this curve will depend on two parameters that we fit together with the cosmological parameters. And then you might also have satellite galaxies that are smaller and just orbit around the main halo. This is how the parametric form looks like for the mean number of satellite galaxies, and this one depends on 3 parameters. So this is a flexible model, but it has loads of assumptions in it that we have to be careful with. Mainly, we've assumed that galaxy formation doesn't impact dark matter clustering. But from hydro simulations, we know that's not true. On very small scales, and within 1 halo scales, sorry, we know that there are effects coming from hydro effects like AGN feedback or supernova feedback. But we will assume here that those are constraints to very small scales. And the second assumption is that the mean number of galaxies depends only on the mass of the halo. But there is evidence pointing towards the fact that that might not be the case. And especially, it might depend on the environment the halo is in. So you might have 2 halos with the exact same halo mass, but living in one an overdense environment and one in an underdense environment, and they could have a different number of galaxies. But this effect is thought to be small. So hopefully in the scales of interest, that is something that we can still ignore. But that is something that will have to be tested in the near future. Okay, so now we do have a way to generate mock catalogs of galaxies. So we can start with simulations that have a set of cosmological parameters and galaxy formation parameters and generate mock galaxy maps. So you can see here 3 different galaxy catalogs for different values of the cosmological parameters, in this case, omega matter. And the question is now, how do we compare what we simulate with the observation so that we can learn something about the cosmological parameters, in this case, omega matter? In the end, we're interested in the probability of omega matter given the observations. And I say the probability because we don't just want a point estimate for omega matter, so we don't want to know that it's 0.312, whatever it is, but we want an error bar to go with it, because we want to check how compatible is the output of this data set with something like the CMB or other probes. And given the maps, we could define a likelihood based on the number density on a grid, for instance, and compare these maps one by one. However, we can't really do that yet. I think it's going to be possible soon, but not yet, especially because we don't know the exact initial conditions that gave rise to this galaxy field. So we know the statistical properties of the initial conditions, but not the particular phases that gave rise to it. So if we were to follow this path, we will have to infer the cosmological parameters, the galaxy formation parameters, and the initial phases at each point. So this is a lot. And this is not the only limitation. Actually, the main limitation is the fact that embodied simulations are extremely slow to run. And if you wanted to evaluate the likelihood of these initial conditions together with cosmological parameter space, you'll need more than 1 million calls to an embodied simulator. That's not something we can do today. I think here is where machine learning has lots of potential to accelerate this problem and make it feasible. But currently, it's not an option. But if you want to learn more about this type of approach, there's a group working on something called BORG, B-O-R-G, that is looking at how we can actually do this. And I think it's super interesting, but it's going to take a bit longer to be able to do that. Okay, so if we can't do that, what we can do is summarize data. So we've already talked about the 2-point correlation function. And I told you that the late time galaxy field is non-Gaussian, so it's not an optimal summary. But we can still extract a lot of information from it, although it's not optimal. Here you can see how it looks like for mock galaxy catalog that I generated. And you see that it's very large on small scales and then decays. Now, the issue is that if we use perturbation theory to predict the value of this 2-point correlation function, we can't really do it in the whole range of scales. So when galaxies are close by, perturbation theory fails because the overdensity is too large. You can see that it works very well on large scales, but that means that currently, what current analysis are doing is throwing away all this data, so not using it at all. And that's a pity, especially because it's the data with the highest quality. So if you look at the error bars, you see how they're larger on large scales and smaller on small scales. So we really are throwing away the best data that we have. And I'm cheating here because you see I have this R subscript on the supercorrelation function. This is because I'm computing it on the real space positions of the galaxies. Since it's a simulation, I can do that. But in real life, we only have the redshift space positions of galaxies. So the two-point correlation function looks like something like this. It's two-dimensional because although the galaxy field is isotropic, when we introduce this particular line of sight direction along which we move galaxies, we're breaking that symmetry. So it will now depend on the distance parallel and perpendicular to the line of sight. And we're going to see its features later on. But the idea is that we need a way to predict how this will vary as we change the cosmological parameters, and perturbation theory is not going to be enough. That's why we look into something called emulators in cosmology, or simulation-based methods in other fields. And I'm going to explain how it works now. Here you have a plot of so we first run a series of n-body simulations. In this case, it's 100 n-body simulations with different values of the cosmological parameters. So here you can see sigma 8 and omega matter, and where the 100 simulations are in parameter space. But of course, the parameter space is larger than that. You have 6 cosmological parameters that you're varying all together within this 100 simulations. So it's very sparsely sampled if you think about this 6-dimensional parameter space and you only have 100 shots at it. But this is the limiting factor is just the speed of n-body simulations. So that's why we only run 100 of them. But the idea is that this is enough actually to get very accurate predictions on smooth functions like the two-point correlation function. So you can then measure the two-point correlation function at each of these simulations and see how it varies for the different parameter choices that we've made. You can see the one inferred from the cosmic microwave background in red, which is kind of at the middle of the parameter space. So we want to see what happens around it. And what we want now is to learn a function f that, given cosmology and galaxy parameters, and possibly redshift as well, produces an estimate of the two-point correlation function that is as accurate as your simulations are. So far, people in cosmology have been using Gaussian processes. And you have here an example of a prior Gaussian process. So Gaussian processes are a model that interpolates over data. Sorry, one sec. And it's a very elegant idea because you're thinking about your function as a continuous multivariate Gaussian distribution. So you can think about what I'm showing here as a prior over functions. So we will assume that the outputs are all multivariate Gaussian distributed, but there is a k t of t prime. This is the covariance that we assume that f will have. So in this case, we're assuming that points in this curve will have a covariance matrix that is inverse to their distance squared. So that means, for instance, if we look at this blue curve, that a point nearby will be highly correlated. But if we look at a point farther away, it would be not correlated. So this is a prior over smooth functions, basically. But if you wanted to learn something like a periodic function, you would choose a different kernel that has that periodicity inbuilt. In our case, what we want is a prior over smooth functions. And you can see these are different samples from the Gaussian process before it's learned anything. You can just see random functions, which doesn't seem to be very useful, right? What makes them useful is the fact that we can condition the Gaussian process on our measurements. So imagine that we measure the black dots. So we can now find what are the functions that are most likely to go through those points by just conditioning. And this has an analytical solution. That's why they're so powerful. And what's interesting is that we're not only fitting one curve through those points, but we find the full posterior or functions. that means we can also estimate the uncertainty of our predictions at points where we don't have the measurements. So Gaussian processes are really very elegant, and the only choices you have to make is a covariance matrix. So what is your prior knowledge of the function that might allow you to build a better shape for the covariance? So the process that it's very easy to give you accurate answers, mainly because you're conditioning on your training data, right? So it's never going to be too far from your training data due to the conditioning that you do. And they have a small number of free parameters. So the free parameters will be inside your covariance matrix. So it depends on the choice that you make of kernel, that will be more or less free parameters. And you'll have to find it by using some optimization algorithms. So those are the pros, but it also comes with some disadvantages. The main one is that they're very slow, and they scale very badly with the training set size. So the scaling is actually n to the cubed. So you have a large training set, you should probably not use Gaussian processes. Also, if you have a large number of input features. So if you have both, then do not go to Gaussian processes. There are ways to go around it, but it's definitely easier with other methods. And this is actually the case I was facing, because I'm looking at the two-point correlation function dependence as a function of redshift, cosmological parameters, LMS. So the training size is quite large, and Gaussian processes struggle to model all those correlations. That's why I've been looking to neural networks. So you have here a diagram of how a neural network looks like. You have an input layer, in our case, the cosmological parameters, curve separation, redshift, etc. And you want to model an output, which for us would be the two-point correlation function, based on these sets of weights. So if you look at each of these circles, we'll combine all the elements coming from the previous layer and perform a apply a nonlinear function to them. So you're basically learning a set of weights, which are here exemplified by the arrows. And you learn them by defining a loss function. So this is telling you how much do you penalize different errors. In our case, we want a mean absolute error between the predicted two-point correlation function and the measured in simulations to be very small. And we will use what's called backpropagation, so computing the gradient of the loss with respect to the weights to update the weights so that we can find a set of weights that make the loss function goes down. Now, there are also pros and cons to neural networks. Definitely one of them is that they're prone to overfitting. So Gaussian processes have a small number of free parameters, whereas neural networks have a large number of free parameters. Now, that doesn't mean that you can't learn a function that doesn't overfit, but it might be harder than in the case of Gaussian processes and take more time. And the main issue is that loss functions can look very crazy. So here you have an example of a loss function in a very low dimensionalized space. So we're only looking at two sets of weights here. And you can see how it has a local minima, saddle points, global minima. So ideally, you want to find the global minima, but that's not always going to be simple. So imagine that you start with a random set of weights that define network A, and you optimize it through gradient descent, but you get stuck at this local minimum. That will be your model. So it might be that this local minima is in your training set, but not in your test set, in which case you're gonna overfit your model. Now you could have started somewhere else and you could end up in the global minima. So is it a question of luck? Well, it's a question of how good can your optimization algorithm be. And people have been studying this now for a long time and coming up with ideas to make this problem go away or be less important than it is right now. I think that this paper here is very interesting, and it looks at ideas of how can we average the weights of the network as we learn the model so that this problem becomes less prominent.
Carol, we have a couple of questions.
Sure, yeah, that's it.
You want to go ahead and answer a question?
So maybe I go first. So Caroline, could you go back for one slide? Yeah. So I think I'm just curious. So you're making a choice of, I mean, you're looking at the correlation function. You could have done the same thing for the power spectrum. And of course, there's also a question of how you weigh things, but at least with the power spectrum, I mean, the same information in correlation function of power spectrum, at least in power spectrum, we know different Ks are independent of each other. Here, I mean, because correlation function is very much correlated across Rs. So, I mean, how do you decide what you want to actually, I mean, how you weigh these, and even if you power spectrum or correlation function, which one?
That's a good point. Well, for the power spectrum, that will also be the case, right? On small scales, K modes are also correlated. So you're hoping that your model will learn that, because you have R as an input as well. So it should learn that those are correlated and that is more strong on small scales.
But choice of that loss function, it seems kind of arbitrary at the end, because depending on, you may get different results depending on how you weigh things, right? That's
true. And for instance, one of the things we've played around with is putting the covariance matrix in here. So you kind of compute the mean square error with the covariance matrix. So it's like computing the chi-square, right?
Yeah.
But it didn't seem to make a difference. So I don't know if it's maybe because the correlation is not that important, or actually it got worse on small scales, right? So the model learned to give less weight to small scales, perhaps because it's more correlated. The covariance matrix is very non-diagonal on small scales. But yeah, I don't think I completely understand why that happens, why it becomes worse.
Okay, cool, thanks.
That's a good point.
Could you explain the basic a little bit more for me? Here, so you give the cosmological parameters, and then based on that, you produce a C, and then you make a guess for a C, or based on data, you get a C, and you keep comparing them and moving. I'm trying to see what is merging to what.
Sure. Let's start with, imagine that you start with a network that has random weights, right? So each of these arrows will have a set of weights that are random. So you will input your cosmological parameters and whatever inputs you want, and get an output that is one-dimensional, which you want it to be the two-point correlation function, but so far it will be a random number because your weights are random. But then you will compute the loss function that will compare your prediction with the value measured in the simulation. And you will average several of these, and with the average, so this is the sum that I have here, and you will use the estimate of the loss function to update your weights. So you will keep changing your weights when you compare your estimate with the true value.
Our goal is to best estimate for the original parameters, right? The omega m, omega. So, so you keep varying them again? I'm trying to see.
Yeah. You keep, so you have these 100 simulations with different parameters. So you introduce those parameters one at a time, or in batches of parameters, and get the estimates.
Okay, so for each of them, for each set of these parameters, you run this and then see in the end which one has the less loss is optimized or best.
Oh, wait. No, but we're not comparing two observations, right? So our goal is to have a mapping between the cosmological parameters and the simulation prediction.
Oh, okay. So comparing to the simulation.
So the parameters that you're fitting is the weights of the neural network.
I see. Okay. So you're trying, at this point, you're just trying to train the neural network, the algorithm. Okay.
On the simulations. Yeah.
On the simulations. Thanks.
Are there any other questions?
Yeah, there is one more question by Andrew.
It's just kind of relating to the previous questions about, in this case, how do you deal with the positional inputs of all the galaxies?
Well, you have here, so you've summarized all the positions of galaxies into the two-point correlation function. So you only know on average at a given distance how many galaxies are away from at that distance. So you don't really have each individual galaxy's positions anymore.
And so you don't feed those directly into the neural network?
You only feed a set of distances at which you want to evaluate the two-point correlation function.
Okay, that works. Thank you.
Any other questions?
Not for now.
Cool. So I'll continue, but yeah, please keep asking questions. That's really good. Okay, so we were with the pros and cons of neural networks. So as opposed to Gaussian processes, they're really fast and they won't scale with a training size set because you don't need to condition, so that the operation we had before in Gaussian processes has gone away. And the number of input features doesn't matter. So your model is going to be able to, as long as you have a training set size that scales with the number of features, then you'll be able to model it. But the cons is that they're prone to overfitting as opposed to Gaussian processes, simply because they have a larger number of parameters. So the same issue of the loss function is true for Gaussian processes as well. But since the dimensionality is lower, they tend to encounter this problem in practice less often. And perhaps con as well would be that they're probably harder to train. So it's probably requires a bit more experimenting to get them to give you accurate results, as opposed to Gaussian processes. But what we found is that we could make them more accurate and faster, as I'll show you later. But now I want to focus the question to move the focus of the question to, instead of how do we emulate it, what should we emulate? And I'm going to argue that we want to create something flexible. So as I said, we want to marginalize our galaxy formation physics. That means we want to have a component that is as flexible as possible. So for instance, we want to be able to change the way in which satellite galaxies are positioned in dark matter halos, or things like that, or maybe model the cross correlations between clusters of galaxies, so very big overdense regions with galaxies, etc. And for that, what we can do is model the clustering of dark matter halos instead of that of galaxies. So the neural network will be trained on statistics of dark matter halos as a function of cosmology and redshift. And then we will analytically perform a weighted sum of those depending on the given set of galaxy parameters. So we're combining an analytical model with a neural network. And also what is very important is that we want to be extremely accurate. So people normally mention the 1% accuracy, but that doesn't really mean much. What we want is to have a model that is as accurate as our observations are. That sometimes means more than 1% accuracy, especially on very small scale. So you remember the plot I showed you earlier, the error bars were becoming very, very small as we went towards smaller scales. So this is a very strong requirement on our model, and it's going to be hard to achieve this 1 sigma accuracy for future surveys, such as DESI. First of all, because our emulator can only be as accurate as the data that we use for training it, so as our n-body simulations are. And the emulator could also need help to model the complex relation between this two-dimensional two-point correlation function and cosmological parameters. So a way we found it to simplify the modeling is to introduce physical models, and in particular to separate the real space clustering. So what happens if we use the real positions of galaxies, and the mapping between real to redshift space, which is here contained in these V values, which are basically the moments of the velocity field. So again, we will have neural networks predicting these objects, and then our physical model will combine them into the redshift space two-point correlation function that we're after. So I'm going to show you a bit on how we do that. So we start from the real space two-point correlation function with this isotropic. And we compare it to the redshift space correlation function. So you see that the clustering has changed along the line of sight. I'll show you later exactly how that happens. But it turns out that we can relate the two through what's called the streaming model of redshift space distortions. With the only thing that we need to know is this object B, which is the probability of finding a pair of galaxies at a given separation. So maybe let me go step by step. So sorry, go ahead.
No, I was going to say that Niesh raised his hand. Do you have a question, Niesh?
I had an idea, but now I realize maybe it's better to talk about it afterwards.
Sure.
Yeah.
Sure, no worries. I'm happy to afterwards. Thanks. Yes, so this string model so much that we have a pair of galaxies at a given pair separation r and moving at a given relative velocity along the line of sight. So when we move them to redshift space, it would be that relative velocity that makes them move to redshift space. So statistically, the way to write this expression is really the streaming model. And the probability of them moving would be controlled by this object V, which is the probability of a given relative velocity along the line of sight. Now, if we look at simulations, sorry, 1 second. In simulations, we can measure this object and estimate it. And we can understand its properties better. So first of all, let's look at what happens on very small scales. So in real space, again, everything is isotropic. But once we move these two galaxies that are moving within a dark matter halo, they're moving very fast in virialized objects, then the clustering along the line of sight will look like it's diminished just because the galaxies were moving very fast. And this is coming from the fact that the pairwise velocity has a high dispersion and heavy tails. On slightly larger scales, what's happening is that galaxies are infalling towards overdense regions. And this infall is producing a scorching effect on the correlation function, which in the pairwise velocity distribution will show up as a negative mean because infall velocities are negative, and skewness in the PDF as well. Skewness comes from the fact that this infall velocity is different depending on the overdensity you're infalling to. So the larger the overdensity, the larger the infall velocity. And therefore you'll end up with these skewed PDFs. And this is exactly what we see in embodied simulations. So here you can see how the PDF changes with scale. So in the first plot, in the first corner, we have very small scales. In the opposite end, we have slightly larger scales, where you can see there's a trend on having skewed distributions and heavy tails. Maybe you can see it better if I overplot the Gaussian distribution with the same mean and variance. So you can see it really isn't a good fit. So, so far people have been using this so-called Gaussian stream model, so assuming this PDF is Gaussian. But on a small scale, so the scales we want to use, that doesn't work out. And we really need to include the skewness and kurtosis. So I'm not going to go into the details of how do we define this blue curve. But the way you can think about it is that we take the mean, variance, skewness, and kurtosis of the pairwise velocity distribution and produce these blue curves. So in a way that we can do this redshift, real to redshift space mapping accurately with the PDF. And it turns out this is very important to distinguish alternative models to general relativity. So I'm going to show you results for two representative extensions to GR. These are FFR and NTGP models, in case someone knows about them. And these models have two things in common. One is that the background expansion, so h of z, is the same as that of lambda CDM. And there is only one free parameter that describes deviations with lambda CDM. Now I'm going to show you what we find in embodied simulations. So here on the y-axis, you have different projections of the two-dimensional super correlation function. So in case you're familiar with it, this is the monopole, the quadrupole, and the hexadecapole. And I'm showing here in the first column, embodied simulations of FFR gravity compared to embodied simulations of general relativity. So the ratio of them. That would be the black dots. You can see that this model deviates most from general relativity on very small scales, so scales smaller than 20 neoparsecs. So this data is normally thrown away, in which case you will fail to distinguish these two models. And something else you can see is that the Gaussian model will also underestimate the effect, or overestimate, sorry, the effect of these modifications of gravity. So you wouldn't be able to accurately estimate the amount of modification you've introduced. Same story is slightly different for the case of DGP, because on large scales, they're distinguishable as well. But on small scales, you will also need to include this higher order moments, skewness and kurtosis, to understand what's going on small scales. Okay, so what we've done so far is split out the modeling of the 2-point correlation function in redshift space into what's happening in real space and these velocity moments. So we have 4 parameters that describe the PDF, and then we have the real space 2-point correlation function. And the only piece we're missing is emulating each of these so that we can understand the relation to the cosmological parameters. So this is what I told you earlier. So we're going to use a neural network to replace each of these ingredients and then use the streaming model to combine them together to produce predictions of the redshift space correlation function. So now this is work in progress. I'm going to only show you some results on real space. So this is the real space 2-point correlation function for dark matter halos for different halo masses. The the dots will be the simulation measurements and the lines are the emulator predictions. And we can combine those to produce estimates for galaxies. So this is an example of a galaxy population that I made up and how you can reproduce the embodied results with the emulator. So again, this is work in progress and I hope we can make the code available soon. But the end goal of the project is still to do the inverse problem, right? We don't want to just predict correlation functions, but we want to use these predictions to constrain the cosmological parameters. And that's what we're working on at the moment. And I'm going to show you just a very preliminary results on the real space correlation function. So this is a completely made up exercise. So imagine that you're given a real space correlation function. The question is whether you can recover the cosmological parameters accurately by running an MCMC. So remember that we started with around 100 simulations, but now we need to have like 10 to the 6 evaluations of the likelihood of this 2-point correlation function emulator. So that's why we can't use simulations in the first place, right? But what you can see here is the constraints on the cosmological parameters, so the PDF on each of them. And in particular, I'm showing 2 different results, one for when we cut the correlation function on 10 megaparsecs, so the minimum scale is 10 megaparsecs, and what happens if we go to way smaller scales to 1 megaparsec. And what you can see is that we can extract much more information. So in this regime, there's a big gain in cosmological information from going to 10 to 1 megaparsec. But again, this is an idealized exercise in which we have mock galaxy catalogs generated from simulations. So there's still loads of tests to be done in more complex scenarios. But closing this chapter, I want to just give a few thoughts on what can we do beyond 2-point statistics. So we know that we're losing information, but how much are we losing by focusing on these summary statistics? Well, the answer is that we don't really know. We don't really know how much information there is. We know there is more because we can look at other statistics and see that they contain information. So for example, here we're gonna see constraints on the bispectrum. So before we were looking at what is the probability of finding a pair of galaxies at a given distance. That defines either the 2-point correlation function or the power spectrum. But we can look at triangles and see, okay, given that you're at its separation, what is the probability of finding another galaxy at a different separation? So for a Gaussian distribution, this shouldn't add any further information. But since the distribution is not Gaussian, we can see how the constraints on cosmological parameters shrink due to adding this bispectrum information. So we know there is additional information that is very valuable, but we don't know what their limit is because you can come up with a different statistic that might add more information than the bispectrum. As another example, this is a very interesting paper that utilizes a scattering transform. And I really like this visualization because you see in the central column different density fields. The first 2 are produced by 2 different cosmological parameters, and the bottom one is just a Gaussian density field. And they all have the same power spectrum, a very similar power spectrum. So you couldn't distinguish them through just the power spectrum. Of course, they look quite different, right? So Shihao Chang and others came up with the idea of using a transform that tries to maximize those differences. And you can see how it changes as you add more non-Gaussianity. But again, we don't know what the limit is. We don't know whether there'll be another statistic that increases the information content. And that's why I'm interested in looking at machine learning for this problem. The question is whether we can take an input and build a neural network that optimally constrains cosmology. And I think the only interest is not to just get the best cosmological constraints, because we might not care so much about the exact value of omega matter, right, of how much we can reduce the error bars. But I think the important bit would be to put the focus on the representation that the network is learning. So can we learn a summary statistic that is optimal and that allows us to interpret what the model has learned? Ideally, this would be useful to compare simulations and observations. So the question I'm interested in is, can we use machine learning to learn about what is missing in our simulations for them to match what we observe? And for that, I think we will have to think more about the structure of our inputs. So when people have used neural networks before in cosmology, they've transformed the density field into an image and used convolutional neural networks. But I think that really goes against how much we can interpret the model. And perhaps thinking of galaxies differently, such as nodes in a graph where we define distances, could really help us and be able to really interpret what the model has learned. And I think it would be very exciting as well is to use this to model cross correlations between different probes. So I focused here on galaxy clustering, but there are other windows to the universe that we should cross correlate with, like lensing. And this is something that analytically is very costly. It's very hard to combine data from different surveys and get joint constraints. But this is somewhere where machine learning could have a big impact. So I'm going to finish here so that we have some time for questions and chat. But I'll leave you with a summary of where I think machine learning is already having an impact on producing nonlinear predictions, but where I think it will have a big impact in the future. Thanks.
Awesome, Carol, that was great. So let's unmute and for a great talk. And if there are further questions, please feel free to ask. Andrew, you want to go first? You don't have any question? So then, Nayesh, you want to go with your question?
Sure, yeah. So very interesting. So one question, this is what occurred to me in the middle of the talk is, why do you go through this middle step of computing the correlation function? Because ultimately what you want is the likelihood of a model. So why don't you just basically use your neural network to model that, or machine learning to model the, I mean, this is going to be specific to your particular survey, but basically what I'm trying to say is for every particular cosmological parameter, you can predict your correlation function, and you could from that you can get the likelihood of your model matching the data. And then what you want is for your machine learning to interpret the likelihood in places where you don't have simulations. So why don't you, instead of correlation function, just do that with the likelihood?
Yeah, that's a good point, and that's actually what some people are doing. I think the major drawback of that is, as you said, that will depend on your data vector. So for each particular survey, you'll have to build a different emulator. And I think there are drawbacks with that in the sense that your training will depend on the particular survey, right? So if you wanted to use the same method with another survey, they're not necessarily equivalent. Also, it's not clear to me that once you compute the likelihood, it's not clear to me that the likelihood will be a simpler function of the cosmological parameters. It might as well be that it's harder to model.
But this goes to the heart of that thing that you don't care about correlation function, you care about 1 sigma error, and the sigmas come from your survey. So so ultimately you want to get an accurate likelihood for that particular survey. And if you have a very different survey that, I mean, probes different scales and different redshifts, then you probably want a different machine learning training for that, because I mean, they're different observables effectively. So even though, I mean, theoretically they're the same because you're modeling different regions of the observable space, it's probably a different optimal training. And then this probably gets rid of the loss function. At least tells you what is an astral loss function that you need.
Yeah, but it's true that, for instance, our model is a function of redshift, galaxy tracers. So in theory, you could apply it to any survey that you can think of. Of course, the error bars of the survey will determine how much you should trust your emulator, right? Or you have some also emulator errors that you should consider. And sometimes for a survey, they might be more or less important. But in general, you can apply it to any survey that you want. Whereas in the case of modeling the likelihood, then that is not true anymore. And again, I'm not sure that, because the likelihood can be a very complex function of the cosmological parameters. So it might be that's easier to model at the level of the 2-point function.
But you see, the thing is, the surveys are much more expensive than machine learning thing. I mean, you don't have too many surveys, but you have, yeah, I mean, that's what I think in terms of cost, it's maybe not that expensive to have different machine learning emulators for different surveys, because that's usually most of the cost. It's not the emulator part. Anyway, that's what I'm thinking. Okay,
yeah,
thanks.
I think they're two fair approaches, but yeah, it's fair to do both, I think.
James, you want to go next?
Thanks. I was just wondering, so you showed plots in Omega Matter and Sigma 8. I mean, how big is your space of models that you're emulating across, cosmological models? What's its dimensionality?
So we're talking about 6 cosmological parameters, and again, 100 simulations. They're centered around the Planck cosmology. So the cosmology is estimated from Planck, and then you move about 2-3 sigma from Planck. That's defines your range in each parameter.
Okay, because I'm sort of wondering, I mean, all of this suggests that the 2-point correlation function is some totally arbitrary function that's arbitrarily complex, and that, for instance, has 6 degrees of freedom, which presumably isn't really true, right? So presumably all 2-point correlation functions in that space occupy some much smaller subvolume, right? They all look the same in some way. So I sort of wonder a bit, I don't know, I mean, maybe that doesn't matter too much, but so I wonder about something like principal component analysis, or about going back and trying to understand, well, what's the actual physics going into making the model? I mean, you showed things like pairwise velocities. You know, suppose you emulated those things across your set of cosmologies instead and realized, oh, well, you know, it's really just the skewness we need to emulate, and then we can forward model it through everything and get the, you know, we wind up with some 2-point correlation function that always looks roughly the same, but the ingredient that's actually changing from cosmology to cosmology is that skewness.
Yeah, exactly. That's precisely what we're doing, right? Because we're emulating the pairwise velocity moments, and so here I'm just showing the real space correlation function, but we're actually emulating them both separately and then combining them to get the redshift space correlation function.
Okay.
But this is ongoing progress, right? So that's why I've showed only pictures of the real space correlation function. So it's a fair question. But yeah, that's exactly what we've tried to do. So we've tried to separate it into the different components and model the cosmological dependencies separately, because it's a simpler cosmological dependency.
Okay.
Once you look at the redshift space correlation function, everything is mixed up. So different scales are also mixed up. You see an integral here, right, over R parallel. So you're mixing the physics in different scales, and that makes it more complicated. Whereas if you split it into components,
I mean, maybe another summary of this is, of course, ultimately, we will not care what the cosmological parameters are. I mean, it's nice to get a better estimate of them, but it tells you nothing, right? They just have some value. Who cares? What you care about, of course, the whole point of the exercise is to understand the physics. So I think getting out the physics of how the velocity, the pairwise separations depend on cosmological parameters is more important than getting out the cosmological parameters.
Yeah, I think that is
right. I mean, that's a fair statement. The cosmological parameters are just what you sell to the public or whatever, but that's not anything anyone really seriously cares about.
Well,
But
you do
Hubble
care about
tension,
them.
there is
Well,
Hubble
no, I
tension.
mean, you don't, like, you would care, you know, if you were measuring the curvature and you found it wasn't zero, you would care about that.
I
Or if
don't
you
know.
were measuring dark energy varying and you found that was not zero, you wouldn't care about that. But nobody cares what omega matter is. It doesn't matter.
Well, but you care about the
It's just a
consistency.
nuisance parameter, right?
No, exactly, right? You care about the consistency of different probes. So imagine that you found out omega matter has a different value from the one observed in Planck by several sigma. That would be important, right? Because that will tell
Right,
you
okay,
that the early
okay.
universe behaves different from the late time universe.
Okay, fair enough, fair enough.
So
Okay, so as a consistency check, fair enough.
exactly, yeah.
Awesome. Any further burning question? Well, if not, let's wrap up here and thank Carol again. And hopefully in the future, we can have you in person.
Thank you.
Thanks again for the very nice talk. And thanks everyone for attending.
Thank you for the questions. Good day.